Alright, it's problem 162. Find peak element, median difficulty. A peak is an element that is strictly greater than its neighbors. Given a zero indexed integer array nums, find a peak element and return this index. If the array contains multiple peaks, return the index to any of the peaks. So you may imagine that nums of -1, nums of n are going to be negative infinity. So element is always considered to be strictly greater than the neighbor outside the array. The solution must be O of log n time complexity. Here, index 2, which is this 3, is the peak because it's bigger than the 2 and the 1. Here, index 5, which is the 6, is bigger than the 5 and the 4, so that's why it's a peak. It can also return index 1, which is the 2, because it's bigger than its neighbors, the 1 and the 1. Okay. So if this algorithm must be O of log n, then we know that it's likely going to involve like a binary search. So if you think about a binary search, let's start with this. So we know that L and R will initially start as length, well, 0 and length of nums minus 1. So put the L here, the R here, so then the mid's going to be here. So then because nums of M is bigger than nums of M minus 1, but less than nums of M plus 1. So we know that 3 is not a peak because it's not bigger than this 5. But we do, and we also know that this 1 is not a peak because it's less than the 3. But we do know that the 5 could be a peak because it's bigger than this 3 here. So what we could do is we could set M, or the L, equals to the M plus 1. And then what if, what if we have an array that's only increasing numbers like 1, 3, and 5? So in this case, the M would be here. This condition would be hit. Then you would set L equals M plus 1. So then the L would be here. So let's see, L was here, R was here, and then now we say L is M plus 1. So then the L moves here with the R. So then the M would also be there. And then, so technically this is hit again, except instead of the M plus 1, it's going to be minus infinity. So even though the M's bigger than M minus 1, because the nums of N is bigger than the nums of M is bigger than nums of N, which is minus infinity, we have this condition here. If M equals length of nums minus 1 and nums of M, nums of N is bigger than nums of M minus 1, then we return M. And then similarly, we got if M equals 0, nums of M is bigger, nums of M is bigger than nums of M plus 1, then we return M. So then we're going to have this binary search here, L and R. Oh yeah, we have this right here. So we're just going to do a loop while L less than R, where we have mid equals L plus R minus L divided by 2. And then we got these conditions. And then we also have to consider the case where, so we'll move this at the bottom where we don't have the special conditions. there's obviously the case where m is bigger than its neighbors, then we just return m. And then what if we have the opposite condition where nums of m is less than the m minus 1 but is bigger than m plus 1? So then in this case, m plus 1 is not a candidate since it's less than the m, but the m minus 1 is a candidate. So then we'll say r is equal to m minus 1. And we have the last condition where, so we got elif. So what have we got? So here is bigger than its neighbors. What if it's less than its neighbors? So then in that case, it doesn't matter. So either m plus 1 could be the peak or m minus 1 could be the peak. We could choose r equals m minus 1 or l equals m plus 1. We do know that if the nums keeps increasing after the m plus 1, at the very end we'll hit this. So then we're for sure going to find a peak. And similarly, if the nums is decreasing until it hits the m, so that way, so if the nums of m minus 1 is bigger than the nums if the nums of m minus 2 is bigger than the nums of m minus 1, then we know that the peak must be in, the part of the nums array with indices bigger than the m minus 1. And then we know the peak must be somewhere there, because if we hit the end, this part will get hit. So it doesn't matter. And then one special condition that we need to take care of is here, these two. So what if, let's just put this here because the 0 comes before the length of nums minus 1. So what if we have m equals 0, but nums is less than, nums of m is less than m plus 1. So a possibility where that could occur is if we have like 0 and 1 as the nums array. So then here, m would be right here. So in this case, it's not greater than m plus 1, so we're not going to return m. So then what we would need to do is, we know this must be the peak, so then we must move the m up here. So we gotta have m plus 1. So so the m could be decreased by just moving the l. So originally we had l and r here. So in this case, we just move the l and the r at this index, and then the m will be here. So in that case, we could say, let's just change this to l equals m plus 1. So we can get l if m equals to 0 or this. Then let's see. So we could move this up here, actually. Have these be else ifs. And then here, so if m is bigger than m minus 1. Okay, so in this case, nums of m would be bigger than here. So what if what if they're both 0 and 0? So in this case, this would not be hit because it has to be strictly bigger. So then this would be hit. So then we move, because we got m equals 0, so the L would be up here. So the m is here. Now m is this. M minus 1 is not strictly less than the m. So what would be the case here? Oh, okay, so we can never have two neighbors being the same. So we never have to worry about this. So, okay, so then this code should work. Oh, we got this condition here. Let's just move this up here so that way all the return m's are close to each other. And then this is basically an else. Oh, even define mid. Oh, I forgot to have this. And passes all test cases. So thanks for watching this video.